Okay. So we're going to start on chapter 14, which is the Central Limit Theorem. Okay? All right, so the Central Limit Theorem is one of the most important theorems in all of statistics, and it's pretty cool. Basically what it says is that regardless of the underlying distribution, the mean is often normally distributed if the sample size is large enough. Okay? So that's pretty cool. Remember, I think I mentioned last Thursday in class that the normal distribution can often be used even if the underlying distribution is not normal. We're going to demonstrate that today. Okay? So now the question is, what is large enough? Okay? And the answer is, it depends on your type of data. If you have continuous data, usually n is greater than or equal to 30 is large enough. Although you need to check, I should say, check the histogram to make sure that it's normally distributed. Because it's not a guarantee, but it usually works. Okay? If you have proportional data, okay, then NPQ, or NP times 1 minus P, must be greater than or equal to 10. Okay? Now the interesting thing is, most people hear that n is greater than 30, they think that applies to everything. It doesn't apply to everything. Okay? It only applies if you have continuous data. If you have proportional data, then this is the rule. NP times 1 minus P has to be greater than or equal to 10. Yes?
Just in the notes, so is binomial and proportional?
Yeah, binomial is proportional. It's the same thing. For this class. It's not actually the same thing, but for your class, that's true. Okay? All right. So let's do a demonstration. This is kind of a cool demonstration. Here's what we're going to do. I'm going to share my screen here. Oh, I'm already sharing. Okay? All right. So let's do, in fact, I'm going to copy my notes here so I don't have to type it. The Stanford-Binet IQ test is normally distributed. Oh, by the way, that just reminds me. It says do a simulation of RAND between 75 and 125. Okay, yes. Is it already up there? Oh, you're kidding. I thought I uploaded them all last week. I'll do that right after class. Okay? So the standard Binet IQ test is normally distributed with a mean of 100 and a standard deviation of 15. So I want to do a simulation with the uniform distribution. So just as a reminder here, let me stop sharing, okay? So if I'm going to do a simulation of random numbers between 75 and 125, when I draw my graph, what should it look like?
Bell curve graph.
Not a bell curve. Not a scatter plot. If I'm doing a bunch of random numbers, it should be uniformly distributed. What does a uniform distribution look like? A box, a rectangle. Okay? So if I'm doing random numbers between 75 and 125, what are my borders here? 75 here. This is
125.
125. How tall is my box? What's the distance between 75 and 125? 50. So this should be 1 over 50. Okay? All right, so just a reminder, we still want to do that. Okay, does this look normally distributed to you? No. Okay? Now let me ask you a question. If you were to figure out, to guess what your mean is, you've got a bunch of random numbers between 75 and 125. What do you think the mean should be? Should be about 100, right? Okay? So we think the mean will be here. Now, according to the central limit theorem, what does the central limit theorem tell me? Regardless of the underlying distribution in this case is uniform, right? I wish I was done that in black. Okay, but it says the sample, the mean is often normally distributed. Okay, so what this is telling me is if I did the mean of X bar, it's going to be normal, it's going to be a bell curve. Okay, the mean of the bell curve, the mean of the X bar is going to be a bell curve, even though the underlying distribution is not normally distributed. Do you believe that's going to happen? If my sample size is large enough. Okay? Now, how large should it be normally? How large should it be? Bigger than 30. I'm going to do it with less than that just to show you a cool thing, okay? All right, so here we go. Okay, so we're going to see if we can prove that the central limit theorem works. Okay, here's how we're going to do that. Okay, so for those of you who have laptops, you don't need one, but you can follow along if you have one. Okay, your numbers will be different than mine, but that's okay. Okay, so if I do equals rand between 75 and 125. Okay, now what I'm going to do is I'm going to copy this over 9 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and now I'm going to go down 100 rows. I'm going to go down to line 101, since I didn't start on the first line. Okay, now do you remember how to keep these numbers from changing? Okay, so if you highlight all your data like this, if you right click and you say copy, and then if you right click again and you say paste special 1, 2, 3, now my numbers won't change anymore. Okay? Okay, so what we're going to do is we're going to pretend that this is, maybe I'm going to move this over here. No, I'll leave it there. Okay, we're going to pretend that this is a school of 900 students. It's a simple random sample. Okay? Now, just to prove to you, remember I told you I didn't like the histogram maker. Okay? I'm going to show you why I don't like it right now. Okay? We know, according to this, what should this look like? What should my histogram look like? A box. Now, watch this. When I use the histogram maker, okay, I'm going to create my histogram maker recommended charts. Maybe I should then do this here. Does that look like what I drew on the board? No. Why not? Well, for one thing, they use these arbitrary weird things. It looks roughly like a box, but this looks really small. Okay? If I had done that myself, it would look more like a box. Okay? And the reason why, we go from 75 to 125, but the histogram maker goes all the way to 130, so it makes this category too small, and it's why I don't like the histogram maker. Okay? So that's why, if you would have drawn this yourself, it would look more like a box. Okay? Does that make sense? So once again, reason number 3 why I don't like the histogram maker. Okay? Sometimes it messes things up. But trust me, if I've done, I don't want to waste time with that because I want to get through the lecture. But If I had drawn that myself, it would look more like a box. Not a perfect box, but it would look like a box, okay? All right, so now, here's what we're going to do, okay? I'm going to prove that the distribution of X bar is a bell curve, okay? Even though the population is, I mean, that kind of looks like a box, but, okay? So here's what I'm going to do. I'm going to find the mean of each row, okay? Now, I told you that my sample size should normally be greater than 30. I'm going to get away with 9 in this case, okay? So here we go. If I do you guys, how do you find the mean? Average, okay? So if I find the mean of this row, the mean of this row is 101. That's pretty close to the 100 I was guessing, right? Okay? I'm going to do that for all 100 rows. So I'm going to copy that down. Okay? Okay, so think of these as 100 different things. So like 101, 103, 98, 96, 104, see? So the idea here is these are going to vary a little bit, but they're all pretty close to 100, right? But we get as high as 104, we get as low as 96, okay? Oh, look, that one's 108. So some of them are off a little, some of them are farther away from 100 than another. Now, I can also figure out what is the population mean. How would I figure out the population mean? You guys should have already answered this question. How did I find the sample mean? What's the Excel command? Equals average. But now I'm going to highlight all 900 students, right? Okay. Now, in my simulation, I wanted it to be about 100. We're going to see how close I am. 99.88. That's pretty doggone close, right? Okay. Now, so the population mean is 99. Now, I got 101, I got 103, I got 98. So these are going to vary a little bit. Now, let me ask you a question. What if I find the mean of my means? Okay. Now, I'm going to do this. Before I press enter, I'm going to find the mean, which is the average command of all of these. Okay. Now, before I press enter, I want to ask you guys a question. Do you think the mean of my means is going to be exactly 99.88, or is it going to be different? Who thinks it's going to be the same? One?
I mean, like, yeah.
Who thinks it's going to be different? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, who didn't raise your hand? Okay, we had a few honest people here. All right, so drum roll, please. It's exactly the same. Isn't that cool? Okay. All right, so what I just demonstrated was the central limit theorem. Okay. Now, what letter do I use for the population mean? Well, I use the letter mu. Remember? So that's the population mean. This is the sample mean. So, and in fact, the mean of all my means is, so X bar is an unbiased estimator of the population mean mu. Okay? So now, the other part of the central limit theorem, what I'm about to prove right now, and I am going to use the histogram maker because it'll do a good job on this one. Okay? On this one, I'm going to demonstrate when I create a histogram out of this data here, these 100 X bars, okay? According to the central limit theorem, what should the shape be? A bell curve. Okay, we're going to find out if this is going to work. Insert recommended charts, bell curve. Does that look like a bell curve to you? A little bit skewed more than I'd like. If I'd have created it myself, it would look better. Okay? because it uses these arbitrary things here. Okay? So I should have you guys create these by hand and make sure that looks like a bell curve, but it should. Usually it looks better than that. Go ahead.
So you say that you were going to use less, we're going to use 9.
Yeah. So each row is 9, right? So each row is a sample of 9. Each row is a sample of 9.
Why did you use 9? Could you use 11?
I could, but you're going to find out why in a minute.
Technically, you
I
should
tried
have
to. I want to keep the numbers nice and easy. Okay.
So you should have 30 though, at least.
Normally you'd have 30 per row. Yes. But I'm getting away with 9 in this case. Okay. Yes.
Going back a little bit, I did the same thing on my computer and I got the population mean and mean means, they're both different. Yeah, they're pretty close to the same. Yeah, I see what thank you.
All right. Now, okay, does that make sense? Okay, so this is what's really cool. Now, I also want to find the standard deviation of the population. Okay? How would I find the standard deviation of the population using Excel? How would I find the standard deviation of the population using Excel? STDEV, which one? The dot P for population, right? And so if I do this here, now remember in my thing, I wanted it to be about 15. We're going to see how close we get. 14.75, that's pretty close, right? Now I'm going to do the standard deviation of my means. Okay. So standard deviation, these are samples, right? So of my samples, now my question is, before I press enter, do you think it will be the same or will it be different than the 14.75 that I got? Who thinks it will be the same? 1, 2, 3, 4, 5, 6, 7, 8. Okay, who thinks it's going to be different? You voted twice. Did you not vote twice? Okay. So you think, so 2 people think it'll be different? Drum roll, please. Oh, it's very different.
What?
Okay.
Man.
So when we talk about, so X bar is an unbiased estimator of mu, but S is a biased, okay, estimator of, what do we call the population standard deviation? What letter do we use? What letter do I use for population standard deviation? It's on your formula sheet. It's sigma. Okay? All right, now there is a relationship. Okay? So if I want, so I've got a biased estimator. If I want to make it unbiased, the unbiased estimator is S equals sigma divided by the square root of n. Okay? So if I take the unbiased S, okay, if I take the population standard deviation in this case, which is 14.75, and I divide that by the square root of how many is in each of my samples, each row? 9. If I divide that by the square root of 9, this is going to be very close to 4.733. We're going to find out how close right now. 4.91. Okay? So that's pretty close. So it's S divided by this, S equals sigma over the square root of n. S means your sample standard deviation. sample standard deviation. Okay? In some books, they write this as sigma of x bar instead of s. Okay? Now, so today I'm going to introduce to you a new formula. Okay? So here's your new formula that's related to the central limit theorem. It's going to be z equals x bar minus mu over sigma over the square root of n. Now, what does that look very similar to? It looks similar to the z-score where I've got x minus mu over sigma. What's the obvious question that the student's going to ask me? How do you know which formula to choose? Right? Okay. Now, one of these has an x bar, one of them doesn't. Oh, sorry, that one doesn't. That one's not supposed to have an x bar. Okay? Okay. Now, here's the rule. If the problem has an n, use it. If not, assume that n equals 1. Okay? If n equals 1, what happens to this? What's the square root of 1? 1, and it just drops out, right? And then this equation is exactly the same as this equation. Okay? So here's the rule that I would say. This is the better formula to use. And then just remember my rule here. If it has an n in the problem, use it. If it doesn't, assume that n equals 1, and then you get this exact same equation that you got the first time. Does that make sense? Okay? So this is the better equation. Okay? All right. So,
Have we haven't plugged this in yet, or have we? Have we?
so we just did.
Okay.
Yeah, so remember when I did this, so my population standard deviation was 14.75.
Okay.
If I divide that by the square root of 9, because each represents a sample size of 9,
That was just that last answer.
then these two answers are very close.
Okay.
Then this becomes an unbiased estimator of that answer.
Gotcha.
Okay? Now, picture, now, whether, okay, so you'll notice here in my, am I sharing? I don't think I'm sharing. Oh, so you notice here on the board, the underlying distribution was not normal, but the sample is normal. Now, of course, if I have a normal distribution, then my sample will also be normally distributed as well. But it's going to have a much smaller standard deviation than the population. So that's why I've got the skinny sample versus the thicker population. Does that make sense? Okay. And the reality is, that's kind of cool, is that even if I have, if this represents my population, okay, see that's a skewed distribution, right? So the cool thing is, if this represents my sample, or my, excuse me, my population mean, okay, my sample is going to be, I didn't draw that in the right place. My sample, x bar, is going to be an unbiased estimator of my population mean, mu, okay? So one of the big important parts, especially from here on, remember the first week of class I had you identify the difference between a sample and a population? And you thought that was pretty easy? And it was? It's like super critical now. You've got to be able to distinguish between a sample and the population. The sample is going to have a much smaller standard deviation than the population. That's why it's got a narrower curve. But the central limit theorem applies in all three of these cases, okay? Now, you should always, when you're doing this, make sure, in fact, this should probably give you a little bit of pause here. When you look at the, when you look at this graph, that's kind of normal. It probably would look better if I had manually graphed it instead of used the Excel function. once again, this is why I don't like to use the Excel functions, because it skews things when it shouldn't. Normally it looks better than that, but this is kind of a perfect example of why I don't like the histogram maker. Sorry, I'm going to lose my voice. I need to go out and talk about this. But this is why the central limit theorem is so doggone cool. Okay? All right, so let's do a problem. Okay? So the problem I'd like to do is, let's say here, I'm going to copy this. Okay, I'm going to open up a new tab here. So this is our problem here. The mean weight gain during pregnancy is about 30 pounds with a standard deviation of 12.9 pounds. Weight gain during pregnancy is skewed right. An obstetrician in a low-income neighborhood obtains a simple random sample of 35 of her patients and determines their mean weight gain was 36.2 pounds. Should the obstetrician be concerned? What we're saying is, are her patients gaining a lot more weight than they should compared to the population? Okay? So, how would you answer this question? Well, you would want to check for outliers, okay? We're just be given some summary statistics, but according to the central limit theorem, this picture here kind of represents what's going on. The population is normally skewed right anyway, but according to the central limit theorem, we're assuming that her sample is going to be normally distributed anyway, okay? According to the central limit theorem, I can make that assumption, okay? So I'm still going to use the normal distribution for the sample, even though the population is not normal, okay? So what equations would be useful for me to figure out the answer of this question? Probably the one with the star on it, right? Okay? All right. So that's going to be the equation I'm going to use. Z equals x bar. Oh, I forgot to share my screen. Z equals x bar minus mu over sigma over the square root of n. Okay, I'm going to underline that, so actually I'll do it this way. So it looks kind of like a fraction. Okay? Now, as we go through here, this may be a useful tool for you to do. Okay? This is the equation you're going to use on all the homework for Thursday. Okay? I'll have that posted up later tonight, along with the lecture. So let's see, the mean weight during pregnancy is 30 pounds. Okay, so this is a good habit to get into. Something equals 30, what is the something? Is it x bar? No, it's not x bar. Mu, why is it mu? Okay, well, both x bar and mu are both, quote, means, not averages. We don't like the A word, remember, okay? It's the mean of the population, right? So this is where you have to distinguish between the population and the sample. That 30 pounds is for the population, okay? And the standard deviation is 12.9 pounds. What is 12.9 pounds? Which standard deviation? Which one? The sigma. Why is it sigma? Because it's the standard deviation of the population, okay? All that first week of class material is really coming home to roost, okay? An obstetrician in a low-income neighborhood obtains a simple random sample of 35 of her patients. What is 35? It's how many patients, right? It's your sample size. What letter do we use for sample size? N for sample size. She's got 35 patients, okay? And determines their mean weight gain is 36.2 pounds. What is 36.2 pounds?
That's the X bar.
X bar. That is also a mean, but it's from the sample this time. This is from the 35 women in her study, okay? And that's all I have, okay? All right, so I've got everything I need to do to answer my question now, okay? So I'm going to plug it into my equation right here. So what's X bar?
36.2.
36.2 minus mu, 30. My denominator, what's sigma? 12.9 divided by the square root of n, which is 35. This gives me a fraction here, I'll underline that, equals the numerator divided by the denominator, which is 2.84. Okay? Now, let me ask you a very, very important question. WWRD.
Draw a picture.
Rick would draw a picture. Okay, let's draw the picture on the board. Now, let me just mention this really quickly. I'm probably going to have you guys do a test in the testing center, and I'll give you some scratch paper. If I forget, sometimes I do, tell them to call me and ask me if you can have scratch paper. You can, but sometimes I forget to put it on there. I used to tell people you can open up paint and then you can draw your picture there. The testing center told me that you can cheat with paint. I don't know how to do that. But apparently students are very ingenious, okay? If you open up paint, they're gonna tell me that you're cheating, okay? Don't open up paint, okay? All right, so we're gonna draw our picture here. So here, I'm gonna draw it this way, okay? What is the mean of my picture? I just converted it to a standard normal curve, right? Well, I converted it to a standard normal curve, so the mean is 0. Okay, how many standard deviations am I away? .84. Okay, do I want the area, I want to shade the area on the left or on the right? We want the right. She should be concerned if they're gaining too much weight, right? If they're gaining 36 or more pounds. If I go back to this picture, here's what's happening, okay? Now I drew this if it was unbiased, but the reality is, okay, the mu in this case was 30 pounds, right? But I got a value, my X bar was 36.2, it was much higher, right? Now the question is, am I in the tail of this? Basically, this is kind of these two pictures now combined to a single graph here, okay? So I'm concerned if the women are gaining too much weight, if they're in the tail. If they're in the white part, I'm okay. Okay, does that make sense? All right, so now, now Excel can also tell me how to find these values. And Excel is exactly like the table that you guys used, okay? It's always going to tell me the area to the left, okay? But I want the area to the right, okay? So if I find the area to the left, the command I'm going to use is equals norm s dist, okay? There's one with periods, there's one without. The one without is easier to use, okay? Norm s dist. It's on your formula sheet here at the bottom, okay? So just a reminder, you don't need to go looking for the help. It's on the sheet. I gave it to you, okay? Norm s is dist of 2.84. This is going to tell me the white area here. The white area here works out to be 0.9977. How do I get the black area? Equals 1 minus that. Okay, this is what I'm going to refer to as my p-value. Okay, my p-value, the area here is 0.0022. Okay, Now you should be able to do this with the chart or with the computer. So since you used the chart on the last homework, I'll use the computer on this homework. Is that okay? Okay, so on my answer key, I'll use the computer. So I'm going to be using the command norm as dist, dist, and then you put in your z-score, whatever your z-score is.
So it's the one with the dot on it? You said there were two.
The one without the dots.
Without the dot.
Without the dots is easier. The one with the dots, you have to put true on the end, and it's okay. It'll give you the same answer. It's just more annoying. Okay? So if I were to convert that to the percent, what's the probability that her women gain 36 pounds when the rest of the population only gains 30? It's going to happen less than 1% of the time, 0.2% of the time. Does that seem unusual to you? Yes.
Yeah, that's
Okay.
pretty up there.
So here's how we're going to define unusual. It's unusual if it's less than 5% of the time. Okay. So in answer to the question, should the obstetrician be concerned? Yes. She should be concerned because her patients are gaining more weight than the population. Okay? So that's your thing. Now, we've got about 3 minutes left. Has anybody noticed that I posted an extra credit assignment?
Yes.
It's the coolest extra credit assignment ever. Okay? This is my Christmas this week. Okay? My favorite week of the whole year. It's March Madness. Okay? So I'm offering you guys 2 extra credit assignments. Okay? I've already posted a video. One of my students last year took a video of me explaining how to fill out the bracket. But you've already done simulations. Okay? So here's it. Here's what it is in a nutshell. Basically, if you go to the assignments here, and it's due tomorrow, and here's why it's due tomorrow. Tomorrow at midnight. Because the first games, actually there's some games, but I don't care about those. The first games begin Thursday. There's going to be 16 games on Thursday. There's going to be 16 games on Friday. There's going to be 8 games on Saturday. There's going to be 8 games on Sunday. This is like heaven. Okay? This is the best. This is the best week of term. So here's the deal. The simulation, so you can fill out a bracket. Okay? Here you go. Here it is. Basically, there's the video from last year, I think. But basically, here's what you have to do. You can fill out a bracket on ESPN.com. You can use any method you want to do to select teams. But as a general rule, for those of you who don't know anything about basketball, okay, there's four brackets. The lower the seed, the better the team. So the Villanova is, I'm going to give you this one. I'm almost 100% guaranteed that Villanova will be either LIU or Radford, whoever they play. The 8-9 game, that's going to be a toss-up, okay? Now, how you can decide here, the number 1 seed has beaten the 16 seed 132 times in a row. The 16 seed has never beaten a 1 seed, okay? Now, the 2 seed versus the 15 seed, the 2 seed has won 124 times, but they've lost 8. So they've won almost 94% of the time. So as you go through here, go ahead and I want you to watch the video. I want you to actually, you can do it one way, just pick any teams you want, and then pick your national championship. Put that in ESPN.com, follow the directions. You get one point for filling it out, 1 point for each of the final 4 teams you get right, 1 point for the final 2 teams you get right, and 1 point if you pick the national championship. Then I want you to do the same thing, but I want you to do it with this here, okay? Fill this out using a simulation. Now, we already did the simulation a couple times ago. There's a video that explains how to do the simulation. Actually, I think there's 2 videos. I'll show them both to you. So you get 3 points for submitting your spreadsheet. So just for trying, you get 3 points. The same rules, 1 point for each final 4 team, 1 point for the final 2 teams, 1 point for your national championship. So that's a possibility of like 20 extra credit points. But that's if you get a perfect bracket, and hardly anybody will. I've never had anybody get more than 3 teams right on the final 4. But that's pretty good, okay? So watch the video. I explain how to do it. It's already up there, and it's a lot of fun, and then we can talk about it next week. So it's due tomorrow because the games start Thursday. So jump on that if you want to do it.